Okay, here's KBYP with hopefully the final installation of messing with the broken capillary on the TXV on the train heat pump. It worked. It worked with air pressure. It didn't work well. It worked with the capillary for the diaphragm and just the brass T with the refrigerant hose outside, basically sensing outdoor temperature, but that's not going to play well with widely varying outdoor temperatures. And what this system is all about, very important to realize, the sealed system pressures mean nothing without considering indoor and outdoor temperatures and humidities. And hallelujah, I unscrewed the cap on the low side. No refrigerant came out. And I know the system isn't empty. So that port's been accessed several times. Maybe it's seated and it's happy. But the point of this little segment is to show you what I did down in here. I've reattached the sensing bulb with a brass 1/8 inch pipe plug. And it should be obvious from there what I did. So all those connections are soldered except for that. And there's a nice sealing cap on there. And I will need to put something on that so this doesn't go like that vibrating. I'll wrap a little insulation around it. But the point of this video is to start the system up in its hopefully finished form. And by the way, it was necessary to charge this since it's now got a big bulb with a large volume of refrigerant in this system being in the bulb. It's now sensitive to the temperature beyond the indoor coil. So when I charge it with about 150 psi, the pressure, the bulb and the T got cold, of course, probably down in the low 50s. And the pressure went down too far to make decent low side pressure on the sealed system. So I had to up the pressure here to about 170. Did that, and then put this inside, put the cover on, ran it, and then reasoned this pressure. Actually, I measured it with a gauge, and I covered this port, this opening off. But that pressure can be reasoned by measuring the low side pressure, because that's the goal. So when the system got cold in there, the pressure in here went down to about 160. Just nice. A little bit higher than it was before. And oddly enough, the pressure here on the low side didn't get much above 130. Why? And it's been hotter. And the reason for that is that there's a problem with this system indoors in that the airflow is not correct. And airflows and temperatures and humidities mean everything. Otherwise, this sealed system has no meaning. Okay, normally I put the gauge on the low side when the system is running. I want to get a measure of the pressure with the system off. It's reading 225, 30, or 245. So if you will get a pressure and temperature chart for 410, then you can see what the outdoor temperature is. I can tell you from reading the temperature gauges inside. I've got outdoor temperature monitors out here. But, there's one under the overhang down there. The outdoor temperature is about 90. Outdoor monitor. One outdoor temperature reading is 86, and the other is 89. Low humidity. And the indoor is 76, and the outdoor temperature reading on the wall just outside here, which is illuminated, is 96, and that reads a bit high. And the point is that we don't get anywhere near the sealed system until we understand the temperature and humidity conditions inside and outside. Outside's hot, pressures will be elevated. The humidity is lower, so there'll be less heat capacity of the air. Very important. The other problem is that there's a cold air return, and there's nothing in particular keeping it from taking air from that register and that register and sucking it right down in the return. That's very inefficient. And that is the reason that the low side pressures are abnormally low. It's got nothing to do with sealed system charge. This system is charged, except for maybe a half to an ounce I've lost in tinkering with it. It was probably just a tad overcharged. It has some residual vapor in it, about 40 psi worth. And I'd lost some checking the high side, which I've given up on because that contains liquid. There's not much point in checking it. But that just recycling that cold air as soon as it comes out of the ducts at 57 degrees makes the low side go down because the indoor entering temperature is way too low. It's not efficient because it's 67 on the floor, but up here at midway up the room, this room tends to hang at 75. So that means this system is not taking the warm air in and cooling it, and that's very inefficient. So I've got to build a chamber to enclose that, and I'll run an inlet up towards the ceiling to force this to draw warm air in. So what we'll find is that when the system starts at a high indoor, that the low side pressure should be higher, and it should drop relatively quickly and run a fairly long cycle. It's been running with this poor return. It's been running about 12 to 15 minutes and about 5 minutes longer than the other similar system in the rest of the house, which is another 500 square feet. So that's poor performance over here. And since it's just recycling cold air on the floor, it's not picking up the warm air in this room and upstairs, so it's not cooling efficiently. So knowing it's going to take a fair amount of time for the low side to do anything, I'm going to start the amp clamp on high current and reach around here and do a cool call, and you'll be able to see the start current. Okay, there's 74. I don't think we caught that, did we? Okay, we're getting 9.6. It was going to about 12 amp with a reasonably consistent run with outdoor up in the 80s and indoor at 74-ish. So the package current, I don't know, take an amp and a half off that, it's about what it was. So I'm going to go out and look at the pressure gauge. And here is low side, slightly elevated, but not bad. It's almost perfect outdoors. Middle of the high 80s, lower humidity. This is ideal beach bum weather. But that's reading 140 psi, and you might be able to see that it's climbing just a bit. It's going to climb as heat is being transferred. And here, with the system operating, we can't just think about pressure and temperature. That is not the point. The point of this is on the enthalpy chart. This is heat flow. So there's the elevated low side pressure due to high indoor temperatures. We got good outdoor motor speed. We got warm air. It's doing something. And I used a photo tack from Harbor Freight to measure the blade speed. It read supposed to be, I think, 1650. It read half that. No, it's supposed to be something like 850. It read twice that because there's two blades. And the time is 2:23. Add about 3 minutes to that, and we'll see what the cycle time is. Package current 11.8. It's been going up to about 12 when it's hotter, and waiting on a 2-degree delta. And there's a good sounding, nicely humming compressor, and pressure's going down. And now about 125. That's probably, let's see how many minutes later it is. It's now 2:31 and 75 degrees, heading for 74. Package current 11 3/4 amp. So all things considered, the current is a bit low, but not because of low charge, because pressure was higher. when the heat load was higher. But last night it was down in the 60s. The house was open, the house cooled off, and the moisture content's low. And if you watch my previous videos and you understand physics, you understand what this system is not doing is cooling air. The system is taking moisture from the air, which carries 6 times the heat capacity of air, and it's taking moisture and heat from the moisture. If you ever live in a desert like we did in Washington State, you know it's futile to try to cool air. It can't be done. That's why they use swamp coolers. So moral of this story, you want to know what the system's doing, measure the current. Don't even open the unit. And it'll be even cooler with an old-fashioned frosty root beer. Remember that? And I put the digital temperature thingy here to measure the entering. I have to come back in a bit when it's had time to change. But that gives a minute for a maintenance topic. Filter. 2025-4 MERV 12. Extremely good filter. This is the one that was in the edition. It's still, you might say it's still serviceable. Not perfectly white. Here's the ugly view. This was a filter in the house. It's not too far from black. And this was due to the smoke in the air over a week, upwards of a particle level of 150. But that filter is bad enough, it's going to start sucking the element in. So if you haven't changed filters since the smoke, at least check it. Because see how deformed that is? This is distorted mechanically because there's enough contamination. Fortunately, that extremely good, almost HEPA filter picked up those nasty particles. We didn't breathe them. The system's working upstairs. It's 74 Fahrenheit. It's cooler upstairs than down. Why? Upstairs register. Upstairs are always hotter. Well, that abnormally cool indoor entering temperature results in an unusually cool discharge temperature, so it's unusually cool up here. But it's still 75 down here. And that's because of the stratification that's occurring because of that cold air across the floor just being returned right back down in the return and leaving warm air by the ceiling. So what to do to help that? Flip on the switch, turn on the ceiling fan. That'll cause air mixing. Air mixing is vital, and it's rarely enough to have just the system airflow to do correct air mixing. And at 243, a discharge of 61 Fahrenheit. When the system's pulled the house down, that goes down in the middle 50s. There's the system. There's the condensate. It's making water, holding steady at about roughly 125. So that's all this I need to see. I'll take the gauge off and putting the caps on with low strength Loctite paste on the threads, because I've declared this unit done. The rubber seals will not hold permanently. They will leak. The rubber takes a compression set. There's minimal sweat. That tells what the humidity conditions are outside. And this system just shut off just before I showed putting the cap on. This was almost too hot to touch. Now I can touch it. And that goes to prove that the heat on this high side line is due to the heat from the work, the heat from the indoor carried through the refrigerant, where that heat comes in this pipe, is compressed to reduce the volume. That's called isothermal compression. It's compressed without adding heat to it, except for some compressor losses. But that heat is condensed in this pipe, so the pipe feels hotter. But as soon as the compressor turns off, that line takes a huge drop in temperature, which proves that it's not the compressor overheating. It's the heat in the working fluid inside. So that's a very important thing to notice. And the time after taking maybe 5 minutes, maybe a little longer, to check outside, remove the gauge, Loctite the cap on, put the covers on, is 2:54. So abnormally long call, but it was the first one of the day from a excessively warm indoor. And at the end of the cycle, as the system was bringing the last of the warm air from upstairs, I could feel some definite stratification The current here went to 12 amp. And there it is, finished, buttoned up as they say, and this video is absolutely proof that all the information that I got from HVAC forums and wannabe experts online was wrong. This system was a gross leaker. I changed the Schrader cores. I charged it R410 VAPOR. Contrary to the liars that said you'll blow the compressor up, it's working perfectly. I charged it VAPOR with the compressor not running, and I repaired the capillary bulb. All those things that they say can't be done. But this goes to show the difference between just a simple mechanical knowledge and my engineering background. And there's a tremendous difference. So hopefully these 3 videos have been helpful. If you haven't, see the 3 previous videos I've done regarding the TXV repair.